This is the 7th AI and Deep Learning for Enterprise meetup. Thank you to Shape for hosting us this evening. More about them shortly. Just a couple of quick things right off the bat. I appreciate this slide's slightly redundant because you're all here, you already know what the meetup is, but yeah, we're AI and Deep Learning for Enterprise. Next up, so slight change to the agenda this evening. We are starting with Shape. Usually our lightning talk will be right at the end, but we're just rejigging things a little bit to make things work for these guys this evening. And then we will have Vinay talking about how to design ML observability for high-risk AI use cases. We'll then take a quick break, and then we'll wrap up the evening with John, Matt, and the rest of the team from Datasparq talking about solving large-scale vehicle routing problems. So without further ado, could I welcome the team from Shape for your presentation?
Sweet, nice. Google Meet presentation, pretty awesome. I'm just gonna hold this, I guess. But yeah, I'm Namit, I'm the founder of Shape. We're a AI startup based here. We're working on AI and data tooling. And what I thought I'd talk about this evening is a bit about our journey and like what we're building now. We've actually been around for about 1.5 years now. This is me. I'll skip through this because you can already see me. But we were working on this product called CollabKit, which lets any sort of SaaS app or product add Figma style commenting to their app with a composable React SDK. So it feels like you built it yourself. Here's a little video about like the product in action. So you get these little Figma style commenting pop-ups, and you can add them to your app in seconds. So we were working on this for a while, and we're doing pretty well actually. Had a bunch of people using it, companies integrated, customers, stuff like that. All the things you'd want when you're trying to build a company. But then a GPT-4 was announced, and like I'd been following, I think from like Text DaVinci 002 onwards stuff and like toying with it. And when GPT-4 hit, at least for me, I was like, well, this kind of changes everything. And I don't think in 3 or 5 years people are going to be buying like React SDKs to add commenting to their apps. They're probably just going to say add commenting and select a screen in some product somewhere. So we decided to bet the company on GPT-4. And as a result, going through this pivot, we're like, what do we build? And one of the problems that I had faced in a previous job was trying to get an answer for a simple query like, how many users signed up yesterday from Poland, or how many people clicked this button in your product. You usually go to your analyst and ask them, it's not in a dashboard somewhere for whatever reason. You ask them, they're like, cool, thanks, come back in a week. And you go back in a week and you have 10 more questions, and they still haven't answered the first one. So sort of wondering if GPT-4 could do this because it's really good at code generation. So we decided to build Shape, which is essentially like an AI data analyst. And what it does is it uses GPT-4 to understand and read a database from a company. And works, plugs into a data warehouse, writes the SQL, summarizes the results, creates charts, all of that kind of stuff. And it plugs into Slack. So this is what we've been working on. And what I thought, probably most interesting for this group of people is to talk about some of the technical stuff. So I can give you a little demo of how it works. But actually for me, like digging into GPT-4 and playing with it, the most interesting things are, if you were to consider like this exponential curve that we're on with LLMs as the invention of electricity. Like it's this new thing that we've discovered, oh my God, it's intelligent. And for me, the fact that it took ChatGPT for the world to realize, hey, this is intelligent, highlights how much of it was just this interface problem. So we had the raw capability and intelligence just sitting there for like over 1 year. In fact, GPT-3 was around for a while, but it took fine-tuning it on 5,000 question answer pads, I think, to build the right first interface that got 100 million people to start to use it and pay attention to it. And it stopped the world, right? Like in every boardroom, all people were talking about after the 14th of March was like, how are we plugging AI into our business? What's happening next? So if that's electricity, then chain of thought prompting is probably the light bulb, right? Like, how many people here have played with, know what chain of thought prompting is? Yeah. You guys haven't tried this out? 1, 2. Okay, cool. All right. LangChain, yes, LangChain is a wrapper around. When people talk about agents, they're talking about chain of thought prompting, and it's a paper from Google last year, and I can show you the code, right? For this. Let's just pull it up. I mean, I'm going to pull up our products code right now, and let's close this. Close all. Let's go to agent. Bump this up. Cool. So here we go. So chain of thought program. This is what enables LLMs, large language models, to reason. So if you want to get them to think in the way we do, which is like step by step, and outline their thinking, it's this 10 lines of code, which powers like AutoGPT, all the agent stuff, our SQL generation. It's literally just saying, think about what you should do and then do it, like seriously. And one of the actions should be one of the tools you give it, and you can give it a bunch of tools and it figures out which tool to pick up. And for me, this was like the most mind-blowing thing, that like after decades of people working on artificial intelligence, it turns out that it's 10 lines of English which get computers to take the biggest leap in thinking the way we do than anything that's come before it. So sort of playing with this stuff, decided to bet the company on it. Now we're building our product on it. This is the core of our product, by the way. It's this little loop, calls GPT-4, and then decides what we've built is just a SQL agent. So it talks to your data and pulls results. I'll show you how it works. So I've got a working version of it in Slack in this channel. And what you can do is just mention shape and say, this is plugged into an e-commerce data set. So it's got products, orders, sales figures, stuff like that. So I can say like best selling products. Let's see if this works. I always hate doing live demos. And it's not working. Great. Give me 1 second. I'm just going to reboot. Attempt 2. Let's try it again. Oh, I know what it is. There we go. Yeah, I needed to connect to my, sorry, 1 second. Here we go. This should work, I think. Yep, there we go. Cool. So give me 1 or 2 minutes, like Shape's doing its thing, right? So what's happening in the background, like what's going on here? Well, the cool thing is we can just look at the logs and see. So if I pull this up, what you have here is it's like, I should find the tables, and I'm gonna, the input I've got is best-selling products, and it's gone through and scored them. And now it's like, okay, cool, I've got, oh, it's actually processing 2 at once. It's listing the tables. So give it a second and it'll start to go through the rest of it.
What is tools here?
What is what, sorry?
The tools.
Tools. So tools are functions that the agent can call to perform a task. And we've actually given it 4 tools. So list the tables in a database, list the schema for tables, run the query, stuff like that. So really straightforward things. And the cool thing is it's figured out that the tables that seem most relevant to the question are the Looker e-commerce order items and the Looker e-commerce products. I should look at the schema of these tables to understand the data they contain. So here it reads the schema. This is the schema of the tables. You know, what fields do they contain? And here we go. It's running it twice, actually, because I entered it twice. The order items table contains the product ID and sale price columns can be used to calculate the total sales for each product. And this is the LLM like thinking out aloud as it's figuring out how to answer the question. So I will group them by the product name and sale price to get the total sales for each product. I'll order it by the total sales in descending order to get the best selling products. I'll limit the results to 10 as per the instructions because we told it 10. So it goes through, runs that. Now it's generating a chart. So that's some like boring stuff. And let's see. Right. Should we look at Slack? Has it got? Oh, okay, cool. So here we now have the best-selling products, and it summed the total sales for each one, and it's generated a chart using GPT to plot the results. So this is something that would typically have taken an analyst 10, 15, 20 minutes maybe, and you can now do this with GPT-4 very quickly. So that's what we're building with Shape. And thanks, I'll take a few questions if anyone has any, but yeah.
Just very quickly, I'm just going to grab a mic so people will actually hear.
Or you can shout.
One, two, 1, 2. Hey, thank you for the presentation. It's amazing. How complex can it go in terms of queries, and maybe you hit some limits?
Yeah,
would be very interesting to hear.
Yeah, you do hit limits. So there is a limit to like how well it can effectively like sort of reason, right? And there are a couple of like public benchmarks on this. So Spider is like a really famous, it's been around for a while, benchmark of like 5,600 SQL queries. So it's like English statement to SQL query. If you're building a traditional natural language query system, you'd go and test it against this. And the top result is GPT-4, which scores 85%. So it can do most basic and medium, like a few joins, like some group bys, complex schemas, pretty well. And if you ask it to do like 8 or 9 joins or something like that, and it's really messy data, then most even humans can't do that in some cases. So it's where it kind of tapers off.
What infrastructure are you running this app on, or is it SaaS or what?
So we actually we sell this as like a self-hosted product. So it's a Docker image that we provide to companies, and then they host it themselves. Usually in Google Cloud or Amazon or something like that.
Have you got any like pre-baked like custom queries which you kind of have a gazetteer look up against? So like like either a vector store against like pre-gen queries where this is the kind of thing you should be looking for. Or
Yeah.
kind of optimize out some of these end join queries where it's like this is going to be a recursive join, please, or a common table expression.
Yeah, totally. Like I think that's something we found along the way is like the product is what I showed you guys is like the quick version where you get the answer straight away. But what we actually sell is there's an inbox where the queries go and then an analyst approves them. And once they approve a query, we store it in like a vector store for
Otherwise, I can see
look
an
up.
Athena bill being incredibly spicy on the end
Yes.
of this query.
Yeah.
Any more questions in the room? Oh, sorry.
Hey, thanks for that. That was pretty interesting. I just have a question around like distribution.
Yep.
And like how in this kind of like AI race, like you've been thinking about that, especially like with this AI kind of data analyst. It would be great to get to learn about that.
Distribution in terms of as a company trying to distribute our product.
Yeah.
So we do things like the oldest possible way. We just like message people, and direct sales is how we distribute our product. So, yeah.
Did that inform like the direction of your product, like the fact that it's in Slack or anything like that?
Yeah, totally. I mean, like the way we figured out, like what decisions to make is based on speaking to, say, about 100 data teams of companies of different sizes and understanding their workflows. And then it's like, okay, cool. They want it in Slack because that's where everyone already is. And there's already a data questions channel in every company that uses Slack. So why not have it slot in there? Yeah.
Sorry, yeah, there's one more question from the back, I think. There we go.
Thank you for the presentation. It's quite interesting. I did some work on something similar. So I struggled with like a couple of technical bits. So maybe like you obviously like built a company on top of it, whereas like I didn't. So like I'm wondering if like if you could go into a little bit more detail about how do you deal with like business rules? So by business rules, I mean, for instance, like I work with some database of like some very big companies where, you know, there is a set of customer numbers that are actually used for tests.
Yep.
So you need to exclude those. But there are more complicated rules.
Right.
And then there are things like, you know,
Yeah.
thousands of tables.
Yeah.
So you cannot necessarily list them without
Yeah.
running out of tokens.
Yeah.
And then there are like even more complicated things which, well, have to do with like things being split across different database types.
Yep.
And kind of the complexity keeps going on. So like, how do you deal with like some of these situations?
So the short answer is like we wait for a particular customer to say they have one of those hurdles, and then we really quickly build a solution for it. For the first one you mentioned, like if there's the table, let's say they have 1,000 tables, very common, right?
Yeah.
And like you can't put in that's where we do a vector retrieval, vector search across the table names and schemas instantly to determine which ones to include. And then we only include the top 3 so that we narrow the amount of information provided to the prompt. What was the other one you mentioned?
I don't know, like for instance, like a simple one, right? So if I wanted to know what's the most popular product sold by a store in New York,
Yep.
there are like 10 different ways of spelling New York, right?
Yep.
So if you query that, like you don't really know what ChatGPT is going to query, right? Like because you're basically requesting a string comparison, and you don't know like
Right.
you know, so like you don't know if
Yeah.
it's NY in the table or New York or
Yeah.
New York capitalized or like, you know, like and we can go on. Like,
Yeah, so we handle it in like, the main way we handle it is actually like all queries go into this approval interface where analysts can go in and check what's, you know, sort of what's occurred. So there's always like a human in the loop. And I think you're going to need that for the foreseeable future with any of these systems.
Well, yeah, for sure.
And then like there are lots of, like for each of those scenarios, as you can imagine, there are probably possible solutions like, you know, let's get the distinct values for like columns like that. Let's figure out how many of them are there. Let's include them in like a step. So it's what we found is like, we built the first version of this in like a day.
Yeah.
And we had it working,
Yeah.
right? Like that's easy. But then like solving these things is actually like where the
Yeah,
complexity
where,
emerges.
like,
You
yeah,
sit there
yeah.
for a while and you got to fix each and every one of these things.
Yeah.
The other thing we found that was interesting is like, you know, if you plug in any analytics tool today, you're going to go and create like data pipelines and, you know, you're going to create some analytics tables. I don't think this is any different from any other sort of BI/analytics product.
Yeah.
You know, so you're going to have to, ideally you do that and start there, and then you go into like advanced territory with, let's just plug it into some like random set of tables and see what happens.
Yeah. No, yeah, I get it.
I think there was one. Yep.
Time for one more question in the room. Anyone other than Ben? No. Oh, one over here at the front. Sorry, is there a question over here?
Not a question, just an observation. So is it fair to assume that it's going to be a self-service BI or self-service analytics sort
Yes.
of tool set solution? Right?
Yes,
Okay.
exactly. Yeah.
That's what I probably was trying to.
Yeah, it's a
in
self-serve.
terms of how
It's like a scale your data team. So like, you know, serve more ad hoc queries to more of your organization. That's like the end goal.
got it. Yeah, more of an observation. Really.
Yep.
One last question from Ben then, before we move on.
Have you got this wired into anything like Superset or any of the other rendering tools out the box so that you can like pre-generate dashboards and things as people kind of request them, so you can build like live widgets? Because like there's tons of these open source tools that exist with really nice APIs, which ChatGPT understands very well. Have you considered like linking them up to Dash and all the rest of it, so you can actually just build?
Honestly, it sounds like you're hanging out in some of our brainstorming meetings. So
well, seriously, let's chat afterwards because this is an area I work a lot in.
Yeah, we'd love to chat about it some more. Yeah.
Awesome. Thank you very much.
Thanks a lot.
So thank you, Namit, for that. Next up, we have Vinay.
Got it. Awesome. Yeah, nice to meet you guys. Namit, so that was a great presentation. So we always believe that BI gonna be driven by conversations. What you guys are doing is fantastic. So would love to track and see how you guys are progressing. But anyway, so let me take a step back and introduce myself and talk about the topic today. So my name is Vinay, and I'm the CEO and founder for Arya.ai. So what we are building is we are building a verticalized AI PaaS, AI platform as a service for banks, financial services, and insurers. We believe that by verticalization, you can actually productize a lot of layers which are specific to the industry. These layers could be safety layers or explainability layers or scalability layers that are very much specific to the industry. So we have been working on deep learning for almost 10 years now. We started Arya in 2013. We started off as open source toolset provider, but later on we quickly verticalized it. One of the common things that we keep on facing when we go and talk to our customers is, what is the explainability behind it, or how easy for them to understand these model predictions, for example. Or how to define accountability, for example. Because we typically deploy AI in very sensitive, very high-risk use cases, be it in a bank or an insurer, helping them to automate underwriting or claims processing or doing auditing, for example. So in such areas, actually more to the model, the layers around the model, which is explainability, auditability, and those are most important for them to get the comfort to productionize these models. So we have been working on a product called Arya.ai, which is an ML Observability framework. So the idea is, if I can build a model using any MLOps or any tool, how can I enable that model being acceptable by all stakeholders? So to be able to build that, one thing is, so these requirements actually came from our customers. Over the course of time, we started building layers and layers, and that's how our end ML Observability tool has been built upon. So the key questions that any sensitive customer or any industry who is into sensitive business ask is, the first thing is transparency, right? Which is, okay, the model is making some predictions, some suggestions, so how do you explain it? How can we make them understand how the model has arrived at that prediction? So first question is transparency. Second is bounded risk. So bounded risk is, okay, I'm productionizing this model in production, but how do I ensure that it's not going haywire? Meaning, it's not going Skynet and creating a lot of losses for me. So how can I create these guardrails around these models in production? So that's the second question that we typically receive. Third is the promised SLAs. What happens is, whenever we productionize any AI solution, you typically see very good accuracies during the testing time period. But as soon as I move that model or solution into production, the model may not be consistent. The model may be drifting. The performance is not consistent, for example. There are a bunch of reasons why the models could fail. So that's not a reliable product for an enterprise, right? So because they are making a humongous amount of investments, they expect consistency from the product. So how do you define the SLAs as a promise? Fourth is the auditability. As these decisions are very sensitive. Our use cases are in financial services, but you can go beyond financial services, like in healthcare, for example, or autonomous cars, manufacturing, where whenever a model is predicting something, it is actually involving maybe financial transaction or maybe direct impact to lives, for example. So in that case, if something goes wrong, then there have to be a clear auditability to understand why it went wrong and how it went wrong. So without auditability, it becomes really, really tough to be able to productionize black box models in production. And fifth is compliance, right? Meaning AI Act is pretty much nearby. if the regulations are coming to defining what can be productionized, what cannot be productionized, then how do you ensure that these models are adhering to those compliances? So these are necessarily not related to model, but these are pretty much important for the success of the models in production, right? And why are these additional layers required to productionize a model? So first, let's dwell upon this idea. So can AI fail in production? The answer is yes. In fact, it's quite common that the models fail in production. So there are many reasons behind this. For example, for traditional ML models, it could be because there is a data drift or model drift, or there is a pipeline issue or data pipelines issue, for example, or the way that it has been built is not appropriate for that problem statement. So there are n number of reasons why the model could fail in production. And LLMs are kind of the buzz of the hour. LLMs has their own challenges, right? So one is hallucination, black box nature, model attacks, data leakage, for example. There are a ton of issues with LLMs as well. So there are many reasons why these models can fail in production. In fact, if you look at the model performance itself, so many people assume that once I productionize a model, it will remain stabilized at the accuracy that I productionized it. But in reality, the model would be actually underperforming or degrading very drastically over a longer period of times and slowly during a shorter period of times. Meaning if you're using the model for a very prolonged amount of times, you would actually see the model degrading quite often. And this is actually proven proven as well. So there is a research paper published that talks about temporal degradation of models. They did an experimentation on around 20,000 odd plus models. They observed that almost 91% of the cases, model performance was degrading over time. So this x-axis, you could see the time period in which the model has been continued to use. On the y-axis, you will see you can see the error distribution, right? In initial phases, the error distribution was quite small, whereas as the time period progresses, the error distribution is more broader. So it is making more errors more often as compared to initially when it is productionized right after the model training, for example. So you could actually experiment this on your own as well. So we did, we showcased this on a classic lending club data. So lending club data is one of the known, well-known. So that has data from 2014 to 2020. So that's almost 7 years of cycle, right? So what we did was we created multiple combinations of train test data. One is we picked up the data from 27 to 2014, and then we tested on the remaining time periods. Likewise, we trained it on 27 to 2015 and tested on remaining time periods. So we picked up different time periods of training data and we tested on the remaining time periods. So you could see that accuracy is more better for the recent models as compared to older models where the accuracy is a little less, right? So this is quite common in enterprises, particularly. As I said, the reasons behind this is the main reason is primarily data drift and concept drift, which is model drift. Data drift is, I may have trained the data on certain kind of data, but as when I productionize the model, I may be getting a very new kind of data sets. So which actually the model is not trained or not informed, right? Then model will definitely make errors in those kind of cases. So that's data drift. And second is model drift. Model drift is the target itself could be changing. For example, during COVID, before and after COVID, right? There is a lot of change in the principles of process. It could be lending or policy issuance. I'm talking, many examples in financial services because we are very familiar with that industry and all. So there is a model drift is when the model target itself is changing over time. So for example, an ideal customer before and after COVID could have changed. Then model will intrinsically will make errors if you continue to use the same model without retraining, for example. So these are two very common issues on why the model failure could happen. And these examples are not hypothetical examples. So these examples are very much realistic and kind of gotten its own PR as well. So for example, you may have heard about ChatGPT, for example. Initially, when ChatGPT was launched in November, there was a lot of buzz around being biased, for example, or leaking sensitive data sets like credit card numbers, phone numbers, email IDs. There was prompt attacks where they could extract that kind of information from LLMs. And then very classic problems like, for example, credit scoring. In Equifax, it was observed that there was a data drift and it was not realized. And they continue to use the model, which actually gave wrong predictions, wrong credit scores for almost 300,000 plus customers. Similarly, Zillow, for example, it is a classic model drift example where they build a predictive model, but the ideal house price before COVID and after COVID was completely different. So that was not embedded back into the model, and that created model drift and started producing a lot of wrong errors, for example. So these are the common examples in terms of how the model fails, and model failure is actually very big and very realistic problem. Second issue is fairness and bias, right? By regulations, for many of these use cases in enterprises particularly, you cannot use biased models. Now the resolution is, before productionizing the model, you would pick up a bias analysis or fairness analysis and try to do if there is any bias in the model or skewness in the model, and adjust that maybe by adjusting the training data or not. So this has been the current resolution, but it was observed that the bias can be a temporal factor as well. So that was analyzing the temporal effects of model degradation. When they analyzed the bias, they have understood that the bias may not be observed in certain time periods, but it could be observed in certain other time periods. You may not be using the bias futures, but the feedback or the data that you are getting could have certain bias in the data, and that could have induced bias into the model. Which means that you cannot use bias analysis as an ad hoc kind of exercise. You have to do that on a continual basis, right? You have to continuously monitor models, not only for data drift and model drift, but also for bias analysis as well. And there are a lot of examples in terms of how bias can cause a lot of issues to the business. One of the case studies was very early on when Apple has launched credit cards. They have observed that there was a bias towards males in terms of credit capacity as compared to females, for example. So this was an observed case study, and there was a lot of PR around this as well. So all in all, while bias analysis is a known issue, but from a resolution standpoint, you have to look from monitoring it in real time, rather doing it as an ad hoc kind of exercise only during the model productionization, for example. So the third biggest problem that we see is explainability, right? This is one of the most important challenge that we see when we productionize AI, any AI model. So typically what happens is whenever you are putting models in production, so there will be model prediction, and along with the model prediction, you can get model confidence if required. And using these two, you can create an additional model output, which is maybe a categorization of the output or something like that. So this is typically a default output from a model, right? There is a prediction, confidence score, and maybe categorization using those two outputs, for example. So this as an output is not at all enough when it comes to decisions like underwriting or diagnosis recommendation, or maybe self-driving, for example, or fully autonomous manufacturing units. In those cases, simply the prediction is not enough. The user wants to understand how the prediction has been arrived, such that they can get the confidence that, okay, the machine has worked in a manner that I'm comfortable. So I can understand how it has worked and how it is giving that prediction. So maybe I'm okay to productionize this system, for example. In fact, if you ask, one of the biggest challenges for LLMs or generative AI in particular to get adapted in enterprises is the explainability, is the black box nature. They are quite tough to explain, while there are challenges like hallucination and all, but from an explainability standpoint, it's quite tough. So this is because there are different stakeholders that gets involved when the use case becomes sensitive. or very core to the business, for example. So in a typical financial services, you would have stakeholders like business owners, risk managers, auditors and regulators who are completely third party and regulated bodies, for example, and then the end customers, right? Everybody has a different kind of question. Whenever a model is making a prediction, each stakeholder has their own questions. Now they would expect that the solution gives the answers in a satisfactory manner to all of them. That's when it gets it gets acceptable by all the stakeholders, for example. Now, to achieve such kind of explainability, it's quite tough basis on the techniques that you use. Some techniques are quite easy to explain, like linear models, for example, or intrinsically explainable models. They're, by design, they're explainable. But when you try to use very much unsupervised kind of techniques, then it becomes quite tough to explain how the model prediction has happened. So this is one of the biggest challenges that we see when we productionize AI, particularly for sensitive use cases. The fourth challenge that we see is auditing, right? Typically in an enterprise environment, when people think about auditing, so there are different kind of stakeholders involved as part of the auditing. So traditional auditing is from the customer side. There could be business team that gets involved, right? Who is part of the process, for example, who will become part of the audit as well. From the auditing team, they simply needs to know maybe the regulatory overview, taxation overview, or process overview, for example. So this has been the traditional auditing process. Now imagine AI being there and becoming the majority transactional player. So for example, let's say I'm using AI for my underwriting. It would probably be processing more number of cases than any of my human underwriter. If that's the case, then the model auditing will also will be part of your auditing as well. So this is what we expect going forward. When the regulations comes into play, then from a regulator standpoint, there will be algorithmic auditors, not simply the business auditors. If that's the case, then you need to start involving your model builders, right? Who is your data science teams or your solution providers, for example, who are necessarily providing that solution. So this skill set is actually currently missing, ability to understand from an auditability standpoint what is required, such that that kind of layers are added in the solution. These are pretty much exclusive kind of buckets. Hence, people are either focusing on primarily auditing from a process standpoint or a model building standpoint. So they're not building models that are auditable today, in short. So this has to change as when regulations and everything else kicks in. And this is also being requested by many customers today. Having an auditability such that there is a clear accountability part for those. And it's not straightforward as well. So for example, let's say there is a regulation that you cannot use biased models, and the regulator is using ad hoc techniques like a sharper line to try to understand whether you have used any those sensitive features in your model or not. Actually, there are ways you could fool sharpen line. You can actually make them understand that you have not used any sensitive data like the gender or ethnicity, for example, and you can fool the auditors from that standpoint. So you could actually do scaffolding attacks and hide your sensitive features from the auditors. So even auditing is not that simple as we think about. It's not simply looking at artifacts and saying that whether all artifacts are as per the requirement of the business or not. It has to go beyond that as well. So simple traditional methods are not good enough from an auditability standpoint. Next is the data privacy, right? So one of the things that we have seen is, particularly from generative AI perspective, there are ways that I could actually get the training data out of the LLM. So there is prompt attacks, for example, or data poisoning attacks that I can induce and get the actual training data from the system. So this problem is there not only for textual generative models, but also for image generative models as well. So that's why Stable Diffusion, one of the prompts was to actually get an image with Jiffy trademark, for example. and that's how people were able to actually get the real data that is used in the models for building these generative AI models. And this problem is that even if you're using traditional deep learning models as well, there is a membership inference attack paper which actually talks about how they were able to identify the training data if you're using a deep learning model on the other end. So these challenges are now completely new, right? Data privacy and data leakage was primarily looked from a database leakage or database access standpoint, not from a modeling standpoint. Now your models can also become a source of your data leakage. Then you need to test these models, how secure they are and how sensitive they are from these attacks, for example. So one of the things people have done to solve this is doing anonymization. So instead of building the models on actual sensitive data, so they try to do anonymizing the sensitive data and then building ML models. But again, now de-anonymization is also a growing topic as well, right? People can able to de-anonymize data as long as they know the column relationships or maybe column names, for example. So this actually opens up a new area, which is data sensitivity, for example. The fifth and final one is the safety of these models. As I said, so whenever you're putting a model in production, it's actually not like a software which is deterministic, meaning a software is very much deterministic. You know that if I give this input, you will get that output, and you are fairly confident in terms of how the software gives you the output. Whereas for ML, it's quite probabilistic. So sometimes you may not be actually anticipating that kind of prediction, and the model can be giving you completely a different prediction which you are not even prepared or you are not even aware about. Then how do you preserve the usage or risk of these models in production? Sometimes I think in 2017 or 18 there was an algorithmic trading attack where one algorithm suddenly started doing different kind of things that resulted in crash in stock market for a brief amount of time and all, right? I know that may be very much look like a very advanced issue, but it can happen in any kind of business problem. Let's take an underwriting as an example. So what happens is when you put an underwriting model in production, maybe for certain segments the model is not particularly confident enough, or model is not particularly accurate enough. Then if somebody figures out that segment, they can exploit and continue to make the transaction happen, right? So then how do you preserve your usage risk, for example? So that's why these guardrails or policies, for example, risk policies, is important to be established. So this is necessarily the outcome of your stress testing. So typically what happens is, you will run your models on humongous amount of stress testing such that you can identify these gaps. Excuse me. Post identifying these gaps, then you can build these risk policy layers that can actually preserve these models from doing something substantially financially negative from that standpoint. So to do this, stress testing is quite important. So whenever you are productionizing a model, it's quite important to understand what is your stress testing criteria, for example. Again, in LLMs, one of the things that we realized was when you look at a lot of open source LLMs, many open source LLMs, what they have done is they have skewed the testing towards overfitting the testing criteria. So it may not be actually that good, but your testing results may look. And when you start using that in production, your model will start failing, right? All in all, you need to have your own testing criteria, your own stress testing criteria, such that you can run any model to these testing criteria. Thereby, you can create your own risk policies. So this is net is what required for AI ML to get productionized in a particularly sensitive use cases in enterprises. Starting from model consistency, where you could track concept drifts, model drift, and bias and fairness, such that your model is consistent, there is no issues in the model, or you are aware about the reason behind these issues, for example. Next is auditing. So for ML auditing, you need more than a simple process, probably frameworks that can capture these artifacts, more deeper artifacts on a prediction level, not just at a model level, such that when something goes wrong or whenever something is required from an auditing standpoint, you're not spending too much time from different stakeholder standpoint. And then from a model safety and model usage standpoint, you need to ensure that you have tested your models well enough from various angles. It could be data leakage, for example, or safety of these models in production and all, and then productionize them. So this is what is going to be becoming a separate layer on top of your ML models. We have a strong belief that model building is going to become quite easy going forward. In fact, it's already easy today, right? I can build a simple a model in less than 5-10 minutes, depending on my training data. But not all models are qualified to go production. And the ability to use these models in production and still be getting a positive ROI is heavily dependent on what kind of ML observability layers that you have today. I'm talking about this from a particularly enterprise standpoint or maybe sensitive use cases where ML observability is going to be the biggest differentiator in productionizing the models. And in fact, that's the biggest differentiator today, right? If somebody tells you that I can use any LLM and I can still be safe, I can still able to explain it, then the problem is not the LLMs, right? The problem is ability to productionize them. So this layer, which is AI safety and AI governance layer, is going to become a standalone product, which is the ML observability product, for example. So that's what we created over a period amount of time for our own products to begin with. Because we are deploying underwriting models, we are deploying claims automation models in financial services. We have to go through all this criteria of questionnaire from the customers, from the regulators before we productionize them, and that's why we created Arya.ai. So I'll quickly give you a walkthrough in terms of what we have done. Maybe that gives you an idea in terms of how we are approaching this problem. So from an Arya.ai standpoint, so we created multiple blocks. We believe that one block is not enough because there are multiple angles from which we have to solve this problem. So starting off with explainability, for example. So unlike using simply sharp or line, which is open source methods and very standalone methods, we use deep learning heavily in our products today. So we actually created a new algorithm called backtrace. In fact, backtrace, which is actually true to model and more accurate as compared to sharper line, because in sharper line, your predictions can change based on some criteria, right? So that's one. So one, we created our own standalone explainability method. And in addition to traditional feature importance, we have done multiple additional explanations. I'll go into the details. So one is explainability. Second is monitoring. So for data drift, concept drifts, bias, and model performance in real time. Third is auditability. So we capture a lot of artifacts during production and even case-wise as well, such that whenever somebody wants to have an auditability on a prediction, they can get those things. And then we have a separate model risk management layer where a user can define these policies or guidelines on top of the Arya.ai, for example. So I'll quickly walk you through the explainability piece, and then I'll open it for questions because there is a lot of detailing for this case study. So one is, so when it comes to explainability, right? So people typically give feature importance as an explainability, which is good. As I said, it also depends upon what you have used to derive this feature importance, because you can use anything to do feature importance, which may not be true to your model as well. So your model may be working in a different manner. You may be using some other explainability algorithm, which is not at all correlated to your explainability model, right? For example, surrogate models as an explanations, for example. So while feature importance is the first explainability approach, but it's quite important to understand how this feature importance is derived. And second, even if you do feature importance, this is not understandable by all stakeholders. Probably a data scientist can understand what does this mean. A feature contributing positively, a feature contributing negatively, maybe a data science team, maybe somebody who has background on Shapley values or feature importance, for example, they can understand how to interpret it. But beyond that, users like regulators, underwriters, common users, they may not know how to interpret it, right? Then it has to be explainable to them as well. So the second kind of explanation that you could look for is something called references as explanations, which is classically known as prototypes as explanations, for example. So I'll give a quick example, right? So let's say I have this question and I asked one LLM to give me an answer for this question. The output from that solution is, an answer with references. This is output 1. And then output 2 is a very detailed answer. And output 3 is again answer with a bunch of references with a combination of sources from internet and also reference papers, for example. So when you typically ask which answer you would trust more, the first comfort comes from references, right? Whenever there is an answer and there is references, then it becomes quite easy to understand where the answer is coming from and what is the source of the answer, for example. Now the next comfort is, what are these sources? Are these sources highly verified sources, or are these sources simply coming from internet where there is no validation, for example? That is second level of comfort. So typically what happens is, whenever you're getting an answer with a highly verified sources, you will probably trust that answer as compared to simply getting an answer. So this is where it gets differentiated. So what it means is, if you could actually give a model prediction along with references where the model has learned that prediction, then you could actually establish some kind of comfort with the user. So that's what we have done as well. So as we do feature importance more accurately and true to model, at least that's the assumption and validation, whatever we have done so far, we are able to figure out from the training data where the model would have learned this prediction. So for example, for a given case, let's say the decision is 784 as the credit score, for example. So we actually package the similar policies from a model standpoint from the training data where the model would have learned this prediction. So this actually serves two purposes. One is getting the confidence to the user in terms of where the model would have come, and second is labeling error. So what we realized is in enterprise data, there is a lot of labeling errors, even though the process is sensitive, very much important to the business and all. There could be a lot of labeling errors. So if you could actually get the similar cases, you could actually validate the labels for them as well. So you could do labeling validation and at the same time give references to the customers at the same time. So what this means is, let's say if a model is making a wrong prediction, you could actually look at the similar cases from a model standpoint and see if there is any labeling conflicts. And accordingly, you can correct the labels and then retrain the model and then improve the model performance and the performance and all, right? So references as explanations actually became one of the powerful explanations for us whenever we are giving model prediction. So while these two are good, one is feature importance, second is references as explanations, they needed much more than that. So one of the common questions when we surveyed the experts was, they wanted to see an affinity in terms of their principles of execution versus the model principles of execution. So for example, if you ask an underwriter, why would they reject a case? Or if you ask a doctor, why would they suggest a surgery as compared to simply a diagnostic process? They have certain steps, right? They may say that I have seen the age of the patient as this, and then I looked at this, and then I looked at this, and then I looked at this. As all of these are this, I'm giving this recommendation. So that's their principles of executing that task. Now, how do you correlate or give an interpretation between the model principles versus the human expert principles, right? We did a small hack. The hack is, so depending upon your explainability method, in our case, as we have our own proprietary method, our feature importance is or additive in nature. Additive in nature as in, if I combine feature importance 1 and feature importance 2, I could get the combined feature importance taken by the model. Same thing, it may be true for some explainability methods, it may not be true in some explainability methods. What we did was, for any given expert task, we asked them to give us their principles of execution as exhaustive as they can. So for example, for an underwriting task in financing, they may have 100 principles, right? And while as in diagnosis, they may have 1,000 principles, for example. So we actually collect these principles of execution for these specific functions, and then we link each of these principles with the features on which they are actually built upon. For example, let's say if there is a principle like this, if there are any public discrepancies and low FICO score is not preferred, and this is a case where an underwriter will reject definitely. So now this is a one principle, right? You can link this principle with the features, like public bankruptcies is coming from public record bankruptcies. FICO score is coming from these two data points. So once you link this features, and when you add the feature importance of these features, you will get what is necessarily the near equal feature importance of the statement considered by the model. Depending upon what is positive contribution, negative contribution, sometimes these statements could also be negatively contributing to the prediction. So whenever the model is making a prediction in Arya.ai, so we configured these in the GUI. So whenever a prediction is made, you could see things like this: a simple textual explanation along with feature importance of that textual explanation. So now when an underwriter is taking a decision, so they can actually see what is the importance of these observations between the model and between themselves, and then they can actually do a correlation. We observe that if versus how the model works, you could actually validate that once you have a very, very accurate elements of these layers. So this is what compiles the explainability for us. And we were able to build this as a plug and play. So you can build the models anywhere. We don't care. You can simply plug in Arya.ai to bring in all these kind of explainability and provide this in real time for each and every prediction. So this is actually differentiated in terms of how well we can convince a user, how can we explain it to different stakeholders in simple English, in statistical method, through references as explanations and all. So this is what we believe is required. One explanation type is not enough based on the use case. You may need more than one explanation. And if all these explanations are supporting one another, that's the best thing that could happen to your product. Meaning feature importance, observations, and similar cases, all three are aligned from an explainability standpoint. Then your model is actually true, your framework is correct, and you could actually have a true to model explanations, which can actually correlate with the expert functions as well. So while we build this framework, these are customizable components. You can use our feature importance to derive multiple things. Like similar cases, you can customize it. Observations, you can add as many as you want, so that you can bring in your own explainability layer on top of the models. So this is one way that we have solved this problem. I'm sure there are multiple other ways, but necessarily what we believe is, while model building is one major task in the journey, but actually the major additional task is how to make your model acceptable by all stakeholders. That is going to be the most important, because you may have very advanced techniques like LLMs, for example, but if you don't have these layers, it may become unusable, particularly for some certain use cases which are very critical, which can benefit out of this and all of it. You can definitely augment it by having a human in the loop kind of steps, I'm sure. But the full potential is when you have something executing end to end, right? To achieve that explainability and other pieces like auditability, monitoring, for example, these components are really important. Hence, as I said, we believe that ML Observability is going to be the biggest differentiator as we go forward. It's not only the ability of building the models, but it's also the ability of using the models in a manner that which is acceptable by the business, acceptable by the regulator, and acceptable by the society, is what going to differentiate for AI in enterprises. So that's all from my end. I'm sure I have talked a lot of things. Happy to take in if you have any questions, guys.
Thank you, Vinay. So we have time for one question before we take a break. Any questions in the room? Okay.
I'll just ask a very generic question. Vinay, this is Ankit here. Fantastic in terms of the level of detail, right? I'll keep it. So in terms of how's the uptake been from end customers, specifically you talked about BFSI, right? And do you have active customers already leveraging it? You don't need to mention the name specifically, but how's the uptake been? Curious to know.
Yeah, Aman, we work with pretty much the majority of insurance industry in India. So all GIs or majority of GIs, which is general insurers in India, are our customers.
Yeah.
And majority of major banks in India is our customers. We have customers in Southeast Asia, Middle East. In total today, we work with almost 68 financial institutions across the globe. And we are now launching Arya.ai, which is the ML Observability piece, as an independent product. Yeah, so we are well adapted and well penetrated in certain geographies.
And that's fab. My question was more related to the latter, the observability product. How's the uptake of that been? I take it's equally acceptable in terms of you've started getting the POCs, etc., right?
Correct. I think one of the good things is, as I said, once you figure out a template for a use case, like explainability, auditability, that is a template, right, for one use case. Let's say underwriting as a use case. You can replicate that quite quickly. And the validation, the proof point, everything becomes quite easy. It's saying that, I can do LLMs for a use case A. You can replicate that use case quite easily afterwards. So we have seen that network effect because we took time to achieve that in customer 1. Whereas once we did that, customer 2, 3, 4, 5, 6, 7, 8, 9, 10 are quite quick afterwards.
Probably I'll take things offline in terms of the conversation.
Sure.
But no, thanks again. And I guess it must be, 1 o'clock there in India?
Yeah, correct.
All right. Okay. Thanks very much.
Great stuff. Thanks again, Vinay. Cool. So for our final presentation of the evening, John Wyllie. Thanks, everyone.
Thank you. Evening, everyone. Are these guys going? Thank you. All right. Tonight, I'm just going to quickly introduce Datasparq and then introduce Kiko and Matt, some of my colleagues, to tell you about quite an interesting project we've done. Just quick introduction to Datasparq. We're an AI business that really combines data science and engineering and design thinking, and we pride ourselves on actually putting AI solutions live and in production and make them operational for people to use in real life. So beyond pilots, beyond proof of concepts, which means you're not doing a great deal in ChatGPT right now because it's probably a bit premature, but all of this stuff the previous speaker was talking about around observability, ML ops, making things resilient is very much in our way of thinking. Solve lots of varieties of problems. I'm not going to bore you with them, but as I say, what's true is that it's all about getting these things live and in production and operational, and we do it across a number of different brands, enterprise, and small, medium-sized businesses. But tonight, we're going to focus on a particularly interesting piece of work we've done, quite impactful. There's building up a bit of reputation in solving quite hard operational problems. A lot of the customers we work with, quite big established businesses with complex operations, and we find a lot of the problem spaces that we're in is in kind of operations research, in pricing and optimization, and actually some of the machine learning and AI techniques in that space are quite interesting, quite challenging, and that's what we're going to dive into. So tonight, I'm going to tell you a bit about one of our customers, big logistics company. They serve many of the supermarkets here in the UK and internationally, and they have multiple vehicles, multiple warehouses. They replenish supermarkets every day. They replenish pubs, so really core to the British infrastructure. And as you can imagine, it's a very complex operational business. For one of their supermarkets alone, they spend over 100 million a year in transport costs. That's fuel, that's HGV drivers, and as you can imagine in the current economic environment, with fuel prices rising, driver shortages, these are huge costs that are only going up. So trying to optimize these and reduce those costs is a really significant high-impact application of AI. So we're going to take you through this example. And just to sort of set the scene quickly, you'll all probably be familiar of sort of big, hard optimization problems, in particular traveling salesperson. If you have, I think, one van and 61 locations, there are more permutations that van can go on to those 61 locations than there are atoms in the observable universe. So this is an enormous search space that you cannot just solve by brute force. You need some very clever data science to search that space intelligently, but you also need some very clever computer science and engineering, because there's no point in spending 40 grand on AWS compute to save 50 grand in fuel. And equally, if I need a schedule to send a van on a route by 9 o'clock in the morning, my algorithm can't run for 3 days. I need to get an answer quite quickly. So lots of different applications here. And I'll just quickly end by saying, again, getting into the science, the difference between a traveling salesperson problem and a vehicle routing problem, and how vehicle routing is exponentially more challenging than traveling salesperson, is because you have multiple vans. Right? If I've got 400 vehicles, 6 depots, and over 1,000 stores to deliver, not only do I have to figure out which van goes to what store, but I've got to figure out, well, do I use one van that goes to every store, or do I use 400 vans to go to a selection of stores, or anything in between? And if, depending on every scenario, then which routes each van go on. So such a huge problem, but some super exciting data science and engineering to solve it. So I'm going to hand over to Kiko to introduce the problem, and then Matt will talk about how we've engineered it.
Thank you. Thank you.
Sit down here and have a read.
Wait, sorry. Great. Thank you. So, yes, I hope John has convinced you about how interesting and amazing this problem is, but I'm going to continue this convincing effort. Our main objective is that the solutions that we provide get into production. This means that the schedules that we generate at some point make it into the client, and they replace the schedules that they were delivering yesterday with the schedules that we are providing them today. And if you have not encountered these type of problems, the meat of the problem is in a lot of the details. So you can think of very theoretical frameworks about this traveling salesman problem, which is a rather academic exercise, and then you move towards the vehicle routing problem, which is slightly more practical. But when you go and speak to the people in operations, there are a lot of entities that are interacting with each other and that actually interfere with each other, and you need to account for all these constraints that are playing together. So here we are putting from some of the main entities that we need to account for. So we have, for example, stores. We need to visit stores at particular times, which is when these stores are open. Trips, you can't make trips that are 10 hours long because drivers want to see their families, and they want to get to some sleep, and they want to eat. So you need to limit the length of the trips. The same with the routes. And then vehicles, for example, they have a certain autonomy and a certain capacity. So this means that for all these different entities, you need to keep in mind that there are different constraints that apply to each of them. And when we are developing, the solution that we have developed tries to incorporate all of these, and they are actually quite custom made. So it's not that you can just go to a library and then implement these particular time windows or these duty allowances that we have for their specific schedules. Great. So I'm going to spend, so the section that I'm going to go through is going to give you an introduction to an algorithm that is called ALNS, Adaptive Large Neighborhood Search, and it's essentially a framework to solve this vehicle routing problem. And I'm going to hopefully give you some insights on why we are using this type of algorithm and how it actually helps us solve our problem. So the vehicle routing problem, unlike problems that you can solve analytically, is not one for which you can find an analytic solution. This means that you need to use some methods to improve on your solution, but you are never going to get to the optimal. So you are fully aware that you are not going to be sure that you are going to get to the optimal. This is, to the best of our knowledge, not possible. So what you can do is you can try to find a local minimum for your solution. This means a schedule that is efficient in terms of kilometers and in terms of driver hours, and you need to iterate and hopefully try to find more and more minimums. As you can see here, we are showing you this global minimum, but we know that we are not going to get there. So we are hoping to get to one of these local minima, and hoping that this is good enough and this is better than what they had in their operations yesterday. So great. So here what you can see is a schedule. A schedule is a collection of calls. So imagine we need to visit 10 stores and we need to deliver a different amount of goods to each of these stores. And we need to decide a sequence of routes. And we can interpret this schedule as a graph. So we have the depot here in the middle, and then we have some stores which are represented with these smaller balls, and then the trips between stores which are just the edges. And you can see that these routes, they are or these trips, they are directed. So we go first to one store and then to the other, and then we end up returning to the depot. But here, just for simplicity, we haven't put the directions. But please keep in mind that in general, the trips, they work in one particular direction. Amazing. So once we have this understanding of our schedule as a graph, the ingredients that we are going to use to cook our ALNS recipe are these different heuristics. We're going to use subgraph heuristics, remove heuristics, insert heuristics, and then we are going to follow these steps to combine each of these heuristics. So what is a heuristic? When you solve a quadratic equation, for example, you have your formula, and then you substitute your A, B, and C with the formula, and then you get your solution for your X, and everything is amazing and beautiful. In this case, we don't have that luxury, and we need to use heuristics, which are basically rules that we think are somehow smart and are going to get us to this local minimum. You can think of them as, for example, if you're trying to load your trunk, you're going to start with the larger bags first and then leave the smaller items to fill them where you can. This is not going to give you the optimal with certainty, but it's a way of filling the trunk which seems reasonable. And this is the type of rule that we are using here. So we are going to use subgraph heuristics, remove heuristics, and insert heuristics, which are not going to guarantee our optimal, but are definitely going to make some sense and give us progress in that direction. And with respect to the steps, so for each of these heuristics, we have a set, and I'm going to go through that briefly. And then we apply them in sequence, and then we observe which heuristics have worked best and update the weights to select them. So imagine the following. So for the subgraph, the remove, and the insertion, we have a set of heuristics. We have different ways of calculating a subgraph, of removing and of inserting, and then we are going to update each of the weights based on how well we do with this. I will go into detail about this later. But just to continue, what is a subgraph heuristic? It's just a way of selecting part of the graph. So when we solve a schedule, imagine that we have an arbitrarily large schedule. Most likely we won't be able to optimize it all jointly. So one thing that we can do is we just select a sub part of this graph, and we are going to work on improving the solution on that part. And this is exactly what subgraph heuristics does. And this is something that is, to our knowledge, is not greatly explored in the literature. So it's actually one of our contributions to this front, and it has worked out really well. Then we have the remove heuristics, which is from this subgraph that we have selected. We are going to remove some trips and stores in the hope that when we reinsert them back, we are going to get a better solution. So in this case, you can see that I'm removing this one, and the rest remains the same. And then we insert them back, and you can see here that we insert them in a different place. And now, suddenly, for the subgraph that we've selected, we have a different solution, right? And the hope is that this solution contains shorter paths for all the stores that we're visiting. You can see that we are still visiting all stores. We are still having routes that start in the depot and finish in the depot, but we are getting solutions that require less kilometers and less driver hours, which is what we care about. So yeah, that's it. And then finally, when we put all these pieces together, we find that we have an improved schedule, because reduce the kilometers. Okay. So as I mentioned, we have different heuristics, and I'm going to go now into give you intuition around what are different subgraph heuristics that we have developed or that we have implemented. Some of them we've shamelessly copied from other people that were very smart and developed them for us, and then others we've developed ourselves, and they work quite well as well. So one of them is just selecting the entire thing. So for some problems, this is good enough. If you have a small schedule, you might as well optimize the entire thing simultaneously because you have more degrees of freedom within there, right? So that's one possibility. This means that for our initial schedule, we select everything. Another one is that we just take a random subset of routes. This means that, so you can see that, as I was mentioning, each of these sequence of stores represents a route, and we can, instead of selecting the 7 routes that we have here, we can select only 3 of them. And once we select these 3 of them, we are going to apply the other 2 steps that I mentioned before, which is we would remove some of the stores from only these routes, and we would insert them back only on these routes. What's the advantage of this? This scales much better, right? If you have a super large schedule, you can't really hope to optimize everything simultaneously. That's why this selecting only a subset is something that is useful to doing sometimes. And then another one, which is an improvement on this, is that you can select a route, and then you can, what we did is develop something that is a pseudo distance between routes, which means that we compute the distances between each of the stores in one route and the stores in other routes, and we take routes that are close by. The intuition here is that if you have routes that are grouped together, chances are that combinations of stores within those routes are going to give you better solutions, because in this previous example, if you removed this one, for example, it is very unlikely that you are going to insert it back in this one, right? Just because they are too far apart, and in general, routes tend to cluster around certain regions. So that's why this one in particular, it worked better, and you will see it later. So, yeah, and in this case, for example, it would be a possibility that this one here, that it's in this route here, if we decided to remove it in the next step, maybe we would insert it back and we would build something like this. So it's just an intuition. It might not happen at all, but that's the reason why this subgraph grouping by distance is something that is interesting to do. And then finally, another one that is related to this one is that now, instead of looking at routes, what we're going to do is we are going to look at specific stores, and we are going to forget whatever routes we had, and we are going to take a store and look at whatever stores were close by. And here the idea is that we are forgetting about what we did so far. So this is a bit more ambitious than the step before, because in the step before we still keep the structure that we had of the solution that we had built, but here we just forget about it and try to build these routes from scratch. Okay, and so finally, what I have here is, so I'm going to try to explain this in detail. I showed you 4 different heuristics for the subgraph: the full, the split, which is that random split, the show graph, which is this one. This is called show split, and then the closest stores, which is the one that doesn't consider the root structure. And what ALNS can do for us, and this is where the learning part, and this is where we would say that the algorithm is learning something about the structure of the problem, is that the weights, which is how likely we are to use one algorithm or one heuristic or the other, is something that evolves over time. So when we start iterating, when we start improving our solution, we start here, okay? We start at the left-hand side, and we give all these heuristics, we give them equal importance, 0.25, okay? That sums 1. And as we evolve through time, some of the heuristics, just because of how they are giving us better solutions, better schedules, they gain more importance, right? And they go, you can see that they go to, in the case above, the one that does best is show graph, right? You can see it, that it's the green line there, and it remains, sorry, you can see that they don't add up to 1 anymore. It doesn't matter. It's just, we don't normalize it, but the important thing here is we look at the one that is largest and the ratio between the largest and the others. So in this case, the show graph is the most important, and the closest source is the one that is doing worse. So that's for one problem, and we tested that in one problem. I won't go into the details around how this one is different from the other. The main thing here is that this problem is smaller than than the problem down here. And in this other problem, which is a much larger problem, the heuristic that worked best was the closest source. And I think this is a really interesting result, because it means that in the way we have implemented ALNS, we have the ability to learn weights and to use heuristics. You can think of any heuristic, maybe later you tell me one, and I can code it for you, and then we can see how your heuristic does, right? And maybe, I don't know, a pink line will appear and will beat all the others, and that would be amazing. But if your heuristic is not good, it will be at the bottom. So there's no discussion here. So you can see that the full graph for the much larger problem is just doing much worse, because it's harder that if you go to this super large problem, that when you try to optimize all together, you're going to find better solutions. So I think, yeah, that's it for me. Just to summarize what I've presented in this section. We have implemented the LNS. This algorithm is not new at all, but in the way that we are encoding it's quite new, because we are incorporating new heuristics. We are making it super parallel, as Matt is going to explain now, and we are solving really, really challenging problem computationally, and it's delivering a lot of value for this client. So thanks. I'll hand over to Matt now, who is going to talk about how we actually do this.
Thanks, Kiko. Yeah, so when we built this, part of the ask was basically to build something that could potentially be productionized, could become an everyday optimizer, because it's not very practical if this takes multiple days to run, where there are existing optimization tools that these businesses are using that they run in a number of hours. So, you know, the algorithm is great, but the engineering challenge was to make it run as quickly as possible, and the thinking was to parallelize it as much as possible. I say parallelism here. What I mean is, because that's not a real word, what I mean is getting as close as possible to the maximum number of parallel threads running or parallel processes running as possible to get as much done in the time. So yeah, as Kiko was explaining, with this algorithm, you can copy your schedule, send it off to multiple processes, and get them to work on it in parallel. So you could have, like, randomly select heuristics for each different process. They could all work on the schedule. Then they need to send the schedule back to the main process to figure out which heuristics worked and which ones didn't. And then you adjust your weights for each heuristic, and then that's how you learn as you go along. So part of the challenge of parallelizing this is that you have to keep sending results back to your main process, which is why you can see in the diagram here. So with time going from left to right, you split out your processes and then you bring them back. So this doesn't necessarily lend itself to distributing on the cloud because you've got to send quite a lot of data back and forth. And if you can't do that quick enough, then it's just not going to be worth it to try to distribute it over loads of different machines. You might want to just keep it all in one machine. But what we found was there's a package called Ray. It's a Python package. Ray is a very generalizable framework for distributing work. So with Ray, you're able to define tasks and just tell Ray to run as many as possible. It can create clusters for you. And you just schedule as many jobs as you want and tell it to run. And it comes with, well, part of Ray is this concept of an object store, which is basically a database built specifically for serializing Python objects and deserializing. And what we found was that the performance is comparable to doing everything in one machine using shared memory. And thanks to basically the speed of data transfer between different virtual machines in the cloud, thanks to this object store, that we were able to get around this problem of all this data transfer slowing down the whole process. So another factor in this is the risk where you schedule all these parallel processes, that one process will hold up the others. So let's say you give them all different tasks to do. One of them finishes in 3 seconds, but one of them is still working after 20 seconds. Suddenly you've got hundreds of other workers now waiting for just one to finish. And actually, we basically just assumed from the start that our heuristics all took approximately the same amount of time to run. But it turns out that was completely wrong. When we visualized what our workers were actually doing, this is what it looks like. So this is basically how long they spend running their heuristics until they're finished. They all spend wildly different times. So you can see a lot of these finish quickly and they're just waiting, doing nothing. There's also the risk that one of them just breaks and it just never sends its results back, and then suddenly you're stalled waiting for ages for results. So we made really small change, and we basically made it so that we set a predetermined deadline of 3 seconds, and when we schedule this task to run, we tell it this timestamp is when you have to finish. And if it gets up to that point and it's not finished yet, we just tell it to stop, send your data back, and if it finishes well before that, we tell it, well, just keep going. You can just run your heuristics again. You can just keep exploring your schedule, which is it's a bit different to like the textbook definition of ALNS. So as Kiko mentioned, you basically have to score your heuristic based on how well it did. We've basically changed that so that it's now scored how well it did given the time it had. So if you've got the best heuristic ever, but it takes a longer time to run, then it's not as good as something that can run really quickly and find some pretty good results. So yeah, I recommend factoring, if you're doing a large parallelization problem, you've got to factor in how long things take to run into the effectiveness of that heuristic. So in summary, our attempt at massively parallelizing this paid off. We were able to scale up to an enormous cluster. We put over 4,000 CPUs in one cluster just to see how high we could go. And yeah, I should say it's not a brute force problem at all. Like as John mentioned, there are more potential solutions to explore than atoms in the observable universe. So we're never going to brute force this problem. But at the same time, the more force you have, the better solution you're going to get. And what we aimed to do was to get to a decent result within 2 hours, because that's like an easy time to work with for us while we're developing this, and also it's something that could feasibly be used by the business day to day. But also, when we let it run for longer, so we do an overnight run, it continues to find better results because it's continuing to evolve and find which heuristics are still working, which ones should it change to. And you can squeeze out like an extra percentage improvement if you let it continue to run. which is quite a lot for these schedules, which are just extremely expensive every day. So yeah, our final result. So this, it all paid off in the end, I should say. So compared to the tools that these companies are using currently to generate their schedules, which are their best effort, they spend months preparing these transport schedules. We were able to find a 2 to 3% improvement, which was achievable for them, so they're actually able to implement it. And we also came up with ideas for them to try for further improvements. So if they were able to flex some of the constraints that they have, there's a lot more benefit to be had. Yeah. So thanks very much for listening.
Thank you very much to the Datasparq team. We have some time for some questions, if there are any questions in the room. Straight back to the back for me.
Thanks for this talk. It's been a while since I've been to a combinatorial optimization talk, which I enjoyed way back. Have you tried reinforcement learning for this problem?
Yes. So you could argue that the learning of the weights is not explicitly a reinforcement learning framework, but it's definitely something that has a reward, which is how much are you saving per schedule, per iteration. So it's not explicitly a reinforcement learning framework, so we haven't formulated it as such, but there is some learning happening within the weights. Is there any way in particularly that you would think about implementing this as RL?
Yeah, I guess there is a direct way where your actions are basically your routes. Which route you choose, your states are, well, the state where each track is and the remaining stages to visit, and the rewards is kind of the negative time it takes.
Yeah,
but then you could do this meta reinforcement learning, which is I think what you're describing.
Yeah, no, definitely. I think, well, we haven't explicitly worked like this, but yeah, it would definitely be interesting to try. Thanks.
I have a question. Is this multi-threaded or multi-process? If it's multi-process, it's not sharing memory, and you need to communicate between processes, right? How does it work?
Yeah. So it's purely multi-processed because it's based around this Python framework. It's not very easy. Python is not great at concurrency, but the whole Ray framework gets around this. So so every Python process has basically got a CPU core to itself, and the shared memory, if you like, is the object store database. So it's not. I guess it treats it as an external database that it can just reach into. I have no idea what spaces in memory are actually shared. That's all abstracted away by Ray.
Thanks.
Any more questions in the room?
Thanks, really interesting presentation. Wanted to ask, how do you see the initial solution? Do you use any maximum satisfiability solution or something like that to start from?
So the most of the time we start with just a greedy initial solution. This means that we have the luxury of knowing that we can start with something feasible, which means, for example, just to give you an example, you could build routes that are just depot to place and come back, right? And you do that for every store. This would be extremely inefficient, but would be feasible, and iterate from there. We do something that it's better than that. Should we move this to production, which is something that we are having, as of now, conversations around how to do it, we would most likely start with the solution that they had yesterday, right, or last week, and then introduce the changes, because you're not going to deliver the same amount of goods to every supermarket every week, but it's going to be very close. This means that you can start with a good solution that you had last week, have the changes there, and iterate from there, and that's going to also save some pennies in computation and some time.
Yeah,
Thanks.
that explains, yeah.
I think we have time for one more question, if there's any. Oh, sorry, Ben.
So currently you're looking at kind of a constraint solver against a relatively good starting point. Like, have you ever tried, so previously I've done a lot of work in this space as well, but so what I found was if you start assuming the initial conditions are actually pretty good, you end up in a very deep kind of local well. How have you kind of modeled jumping out of that well? Maybe because of like, we found that if you actually drew all of the tracks around the outside of a city in bigger loops, you actually found much better solutions. But it required an almost clean modeling space to start with.
Yeah.
Otherwise, you end up hyper-optimized into this kind of local maximum region-based things because the clustering just takes over really rapidly.
Yes. So this algorithm is the name. So we always say ALNS, but it's adaptive large neighborhood search, which means that you go to a large neighborhood in the hope that this large neighborhood is good enough to take you out of this huge valley, right? You don't have any guarantees for that. It's true that we have tried with different starting points and we end up with pretty much comparable results. So we are not getting 2 percentage points change between solutions, but maybe 0.3, which is not ideal, but it's something that you can work with. So, and you don't have the luxury. So what we found is that it's better to spend more time going deeper with the solution that is best, rather than spending time with 10 initial solutions that might be quite far away from each other, because you end up with comparable results.
And then just a quick follow-on on that. Do you ever find that the actual customer requirements often end up trumping what will be a true optima, because they want routes that look reasonable rather than necessarily being optimal?
Oh, yes. Okay, yeah.
Because this was the number 2 problem I had.
Yes. What happens is that when you are in that situation in which, this doesn't look reasonable, it means that there's some operational constraint that you've missed, right? So if you have the operational constraints, which means the time windows or the driver hours, or if you have all these in place, they are going to look reasonable. And we've found this because, in fact, there are, for example, in these problems that I was showing, we had maybe like 200 routes, right? And we had an overlap in some of them, and then some others, they told us, oh yes, in this bit, you had this improvement, which we hadn't catch, but it doesn't mean that our solution looks radically different, because they also know what they are doing, right? So they are not new to this, so yeah. So they are going to have the confidence because they have similarities, but they also have improvements in some parts of the schedule.
Okay.
Thanks again to, Thanks again to Datasparq.
Thank you.
So, just before we wrap up, I'd like to say thanks again to Shape for hosting us this evening. And thanks always go to Demon, the longtime sponsor of this event. Just a couple of bits of housekeeping before we head off. The next event will be on the 14th of August. We have some really exciting talks lined up, so please do come along. Venue yet to be confirmed, but coming out very soon. The invite will be out next week. If you're interested in the intersection between AI and neuroscience, please do come along, because we have a professor of neuroscience coming to talk about some very exciting stuff. Just one last thing before we go. We would like to put Shape's offices back to rights for them before we leave. So if you'd like to continue your conversations this evening, there does seem to be a very nice pub over the road. So I ask that in the next 10 minutes or so, if you could head over there, if you'd like to stick around, or wherever you like. Obviously, you're free to go home if you also choose to. So we can just tidy things up here. That would be great. Thanks all, and thanks for coming.